Hello students, welcome to yet another video lecture. In the previous lectures, we have been discussing about approximation algorithms, and the topic for today's lecture will be the vertex cover problem. Before we start, we have to know what the vertex cover is. So let's start with that. Vertex cover. Given an undirected graph, if we have an undirected graph, the vertex cover is the subset of vertices such that for every edge UV, either U or V are in the vertex cover. So if we have any undirected graph, the vertex cover will be the subset of vertices such that for every edge of the form UV, either U or V will be in the vertex cover. Now, this is the vertex cover. What the vertex cover problem is, let's define that. It's related to an undirected graph. Given an undirected graph, the vertex cover problem is to find the minimum size vertex cover. So the vertex cover problem asks us to find the vertex cover of the minimum size. That means the subset should contain the least number of vertices in it, covering all the edges. Given an undirected graph G of the form VE, where V is the set of vertices and E is the set of edges. And what's the vertex cover problem? We have to find the minimum subset C, which will be a subset of obviously the vertices, the set of vertices given, such that C covers all the edges in E. So the vertex cover problem is if we have given the graph G of the form V and E, where V is the set of vertices and E is the set of edges. We have to find the minimum subset C such that C covers all the edges in E, which means that is every edge that is in E is incident to at least one of the vertices in C. So if you take any edge of your graph, the vertex cover set, the minimum vertex cover set will contain a vertex on which this edge will be incident to. This is the vertex cover problem. The graph is of the form this, where the vertex set contains A and B and the edge set is empty. There are no edges in the graph. Now, the minimum vertex cover for this graph will be an empty set. There is no MVC for this graph. Again, let's take another example. We have another, let's delete this edge. Okay, we have another graph defined by the vertex set A, B, C, and D, and the edges are, what is the edge set here? The edges are AC, BC, DC, and BC, DC, and AC. Okay, 3 edges. Right? What will be the minimum vertex cover for this graph? Okay, let's see. It should be C. This is the minimum vertex cover. See, if you take any, this will be our minimum vertex cover. See, if you take any edge from this edge set, take any edge. For example, let's take AC. Now, the vertex cover, minimum vertex cover, it contains one of the vertices on which the A is incident, that is C. Same is the case with BC and same is the case with DC. So, C becomes our minimum vertex cover. If I have a graph like this, and my edge sets are defined as this, the minimum vertex cover for this set, graph should be, it should be C, B, or it can be C, A. See, so the minimum vertex cover, it includes either this and this, or it includes this and this. Because you see, CB will cover all the edges in this graph, CB. So B is B has an edge which is BA and BC, and C has edges BC, CE, and CD. That means the vertex cover CB, it covered all the all the edges in the graph. Same is the case with if we take CA. A has the edge, or A has an edge which is incident, B has an edge which is incident to A. So AB edge will be covered, and C covers the edges CB, CE, and CD. This is the minimum vertex cover for this graph. The problem with this vertex cover problem is that there is no polynomial time solution available for this problem, for solving this problem, because this problem is a known NP-complete problem. And from the previous lectures, you should know that if a problem is NP-complete, that problem cannot be solved in polynomial time using a deterministic machine, right? So that's why in the previous lecture we touched the approximation algorithms, and there are some efficient approximation algorithms that can be used to solve this vertex cover problem, which asks us to find the minimum vertex cover. Now, the first step of this algorithm will be to initialize, again this is the approximation algorithm for the vertex cover problem. Initialize the result set as the empty set. Now the second step will be consider the set of all edges in the given undirected graph and let's call this edge set as, let's name it as E, right? Third step. While E is not empty, we have to do the following. While E is not empty, do the following. What? Step number A. Arbitrarily pick an edge from the edge set of the form UV. Arbitrarily pick any pick any edge UV from the set E. From the set E. And when you picked an edge from E and add U and V both to the result set here. So we picked an edge arbitrarily. Now we will add these vertices in the edge U and V. We will add these to the result set, this, right? After adding the vertices U and V to the result set, what I have to do is I have to remove all the edges from E which are incident to any of the vertices in the result set. And our fourth step will be returning the result set, which will be our minimum vertex cover set. Now after adding U and V to the result set, what we'll do is we'll remove all the edges from E in which which are incident to any of the vertices in the result set. Any of the vertices which are already in the result set. We have to remove all those edges. And finally, when the set E is empty, we'll return the result set. That's our approximation algorithm for vertex cover problem. If I have a graph defined as G, V, E, where again V is the set of vertices and E is the set of edges, and I have to find the minimum vertex cover set C, which will again be a subset of V. I have to find this C. Now, step number 1, what I'll do is I'll initialize C. So by initialization I mean I'll make a set C and I'll initialize it with phi. So C is empty at the start. After that, what I'll do is while E is not empty. So while E is not empty, while there are still edges in our edge set E, what I have to do is pick any edge UV arbitrarily and put U and V in the result set C, the minimum vertex cover set. So this will be C union U and V. And after that, what we'll do is delete all the edges in E which are which are incident to any of the vertices in C. And step number 3 is return C. This will give us the minimum vertex cover for our problem. This is the approximation algorithm. Let's test it on some graph now. Given as this A, B, C, F. This is the vertex set of my graph, and my edge set is like this. So my graph G, it's defined by VE, and my vertex set V, it contains A, B, C, D, E, and F. And my edge set E, it contains AB, it has BC, it also has BD, it has DE, it has CE, and last it has CF. This is my edge set and this is my vertex set. Now my minimum vertex cover problem or vertex cover asks me to find a subset of this vertex set which will cover all the edges in the edge set. So let's again use our approximation algorithm and see how it solves our problem here. Let's say we arbitrarily pick the edge BC, this edge here. So when we pick this edge BC, right? First step is we picked BC and edge set contains this, we picked BC. Now we will put B and C both in our result set. Let's call that result set C. So my C will contain B and C. This is my first step. And the second part of my second step is to remove any edge which is incident to any of the vertices in our result set. So the vertices in our result set right now are B and C. We have to remove any edge which is incident on either B or C. So this edge is incident on B, this edge is incident on C, this edge is incident on B, this edge is incident on or to C, right? So we have to remove AB, we have to remove your BD, we have to remove your CE, and we have to remove your CF. And BC we considered BC, it's already removed, right? We took BC, it's already removed, right? Now the remaining edge there is DE. Now after picking DE, our result set here, it will give us the minimum vertex cover. So our minimum vertex cover after picking DE will either be B, C, E, or it will be B, C, and D. Any of these sets is the answer or the solution to our vertex cover problem for this graph. If you look at these three vertices closely, B, C, D or B, C, E, these three vertices will cover all the edges in the graph. See, first, let's take B. B covers the edge BC and it covers the edge AB and it covers the edge BD. Done? And our C, it covers the edge BC which is already covered. It also covers the edge CF covered. It also covers the edge CE covered. Now after that we can either use E or we can use D, which will cover DE. And this is our minimum vertex cover for the graph. Right? Let's take one small example to finish things up. If this is my graph, this is the graph. The graph is defined as G, V, E again. The vertex set for this graph is A, B, C, D, E, F, G, H, I. F, G, H, and I, right? A, B, C, D, E, F, G, H, and I. And my edge set is given as, what's my edge set? My edge set here is, it's AB, it's, this is done, it's BD, it's BG, this and this is done, it's DE and DF, DE and DF, right? And it's EF, it's BC, it's GH and GC, GH and GC done, it's CH and CI, and lastly it's HI. So my edge set contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12 edges. Let's see if there are 12 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12 edges. Now again, let's use our approximation algorithm to get the minimum vertex cover set. Let's arbitrarily choose any edge from this edge set. Let's suppose we'll choose the edge DF. Let's choose DF. So if C is our vertex cover set, then our C will contain D and F, right? And we have to delete and remove all the edges which are incident to either D or F, right? So I have to remove this and this and this, because D, and I have to remove this too, because D has 3 incident edges, DB, DF and DE. I removed those. So DB or BD and DE, DE this and EF this. We have to remove these, right? After that, if I choose arbitrarily BC, then I have to put B and C in here, and I have to remove all the edges which are incident to B or C. So I have to remove this, 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 this and this. So for now, I have D in my C, this minimum vertex cover set. I have F there, I have B there, I have C there. Now remains the GH edge and HI edge. If I consider this, then I'll get H in my minimum vertex cover set, which will remove this edge, and I'll get the final answer as DFBC edge. or FDBCH, which covers all the edges of my graph, and it is the solution. The solution is DFBCH to my problem. So the lecture was about, actually it's related to our previous lecture, approximation algorithms. We saw in the previous lecture that there are many problems, many problems which are NP hard or NP complete problems, and the solution to those problems, the solution in the polynomial time using a deterministic machine is not possible. So that kind of demotivated us as computer science students or as engineers and scientists, as mathematicians, on how we can solve these problems if those problems cannot be solved using a deterministic polynomial time algorithm. That's why scientists came up with the approximation algorithms. The approximation algorithms, they solve these NP hard problems, NP complete problems efficiently. May not be optimally, they may not give the best solution, but they solve the problems efficiently. And one such problem we discussed today was the vertex cover problem. In our vertex cover problem, we have to find the minimum vertex cover which will cover all the edges of a graph. We saw that this is a known NP complete problem, and a deterministic polynomial time solution to this problem is not possible. That's why we took an approximation algorithm which solves this problem quite efficiently, and our work here is done. Thank you so much.